40 trillion gallons of water press against Hoover Dam at 315 pounds per square inch. You would assume millions of tons of concrete is what holds it all back. It is not. Nearly 90% of that crushing force is redirected somewhere most people never think to look. And without that hidden transfer, this dam would have failed decades ago. Textbook diagrams have misled generations. They show Hoover Dam as a blunt wedge of concrete, a monolith planted in the canyon, holding back Lake Mead by sheer bulk. The story sounds simple. Make it heavy enough, and nothing can move it. But the reality is far more subtle and far more ingenious. In 1935, John L. Savage, chief design engineer for the U.S. Bureau of Reclamation, put the confusion to rest. In his own words, "The Boulder Canyon project, as presently designed and being constructed, shall be classified as an arch gravity dam of the concrete type. The arch action furnishes the primary resistance to water pressure, while the gravity component provides additional stability against overturning and sliding. Consequently, the structure must be analyzed as a combined arch gravity system rather than as a pure gravity dam." This was not just a technicality. Savage and his team understood that the dam's true strength came from its shape and its setting. The dam's sweeping curve presses against the canyon walls, turning water pressure sideways into solid rock, not just down into the riverbed. The concrete, about 650,000 cubic yards in total, is massive, but it is not the only player. The arch action is what lets the dam survive forces that would shatter a simple wall of concrete. The difference is not trivial. At the base, water presses in at over 300 pounds per square inch. That is more than 20 tons per square foot, multiplied across a wall 660 feet thick and 726 feet tall. If the dam relied on gravity alone, the structure would have to be even bulkier, wider, heavier, and far more expensive. Instead, the arch gravity design allows a thinner profile and channels most of the force into the abutments, the canyon's nearly vertical sides. Savage's memo did not just clarify the dam's classification, it set the standard for every calculation and safety check that followed. The official design manual, cited in his memo, required engineers to analyze both arch and gravity effects together. This approach shaped not only the Hoover Dam, but also the future of large dam engineering worldwide. The myth of brute force concrete falls apart under the weight of these facts. What really holds back trillions of gallons of water is a precise balance of geometry, geology, and human calculation. The dam is not just a wall, it's a three-dimensional lock, wedged between ancient cliffs, designed to transfer unimaginable pressure away from concrete and into the bones of the earth itself. The true scale of what Hoover Dam holds back defies easy comprehension. Lake Mead, the reservoir behind the dam, can store more than 32 million acre-feet of water, about 40 trillion gallons at full capacity. That's enough to cover the entire state of Connecticut in water almost 10 feet deep, or to supply every home in the United States for nearly a year. But the real story is not just about volume, it's about pressure. How the weight of that water presses relentlessly against the dam's face, hour after hour, year after year. Water pressure doesn't build evenly from top to bottom. It increases with depth, so the deeper you go, the greater the force. At the base of Hoover Dam, where the water column reaches nearly 725 feet, the pressure reaches 315 pounds per square inch. That's more than 20 tons pressing on every square foot of concrete, multiplied across a wall that's 660 feet thick at its base and stretches more than 1,200 feet from canyon wall to canyon wall. The total horizontal thrust generated by the water is measured in millions of tons, a force so great that it would flatten almost any structure built without a plan for redirecting it. The numbers become even more staggering when you realize how that force is distributed. Roughly 90% of the water's thrust is not simply pushing against the dam's weight. Instead, the arch gravity design channels that pressure sideways into the solid rock of Black Canyon. The dam's curve transforms what would be a crushing, direct blow into a sweeping lateral push, turning the canyon itself into part of the structure. Only about 10% of the total force presses directly down, relying on the mass of concrete to resist sliding and overturning. The rest is carried by the canyon walls, which act like the jaws of a giant vice, clamping the dam in place. This is why the engineering challenge was never just about pouring enough concrete. The real test was finding a way to manage forces that, if left unchecked, could rip the dam from its foundation or burst it apart at the seams. Every calculation, every design decision, every cubic yard of concrete was shaped by the need to control and redirect this unimaginable load. The dam's survival depends not only on its size, but on the precise balance of geometry and geology, a balance that must hold steady against the weight of 40 trillion gallons, day after day, decade after decade. Beneath the sweeping concrete face, a labyrinth of tunnels and hidden passageways forms the dam's nervous system. 4 diversion tunnels, each 50 feet wide, once channeled the Colorado River around the construction site, a feat that required blasting through nearly 3 miles of solid canyon wall. Today, more than 15,900 feet of inspection galleries snake through the dam's body, some buried over 50 feet deep. These galleries allow engineers to monitor the structure from within, checking for leaks, movement, or signs of stress that could spell trouble in the future. But it was heat, not water, that nearly broke Hoover Dam before it ever held back a drop. As the concrete was poured in massive blocks, chemical reactions inside generated enough warmth to threaten the dam's integrity. Without intervention, the core would have taken over a century to cool, and the resulting thermal stresses would have split the structure apart. Early cracks, some as wide as 2 inches, appeared in the upstream face, sending a jolt of anxiety through the engineering ranks. One foreman, standing inside a newly poured gallery, described the sensation as like working in a bread oven. The solution was as ambitious as the dam itself, a network of 582 miles of steel pipes embedded within the concrete. Chilled water, pumped through this maze, drew heat out at a rate of 1,000 gallons per minute. The system's refrigeration plant produced 1,000 tons of ice daily, keeping the temperature rise within a safe 30 degrees Fahrenheit above the river. In just a few months, this hidden cooling web turned a century-long risk into a manageable challenge. The cracks were grouted, the threat neutralized, and the dam's skeleton of tunnels and pipes became a silent guardian against the forces inside and out. 96 men lost their lives building Hoover Dam. The official accident logs list deaths from falls, rock slides, heavy equipment, and even carbon monoxide in the diversion tunnels. Each loss was documented. The stories of bodies entombed in the concrete are legend, not truth. Construction records and daily logs confirm that every worker who died was recovered. No one was left inside. Engineers knew any foreign object, even a body, would weaken the concrete and threaten the dam's integrity. The myth persists, but the facts are clear. The human cost of Hoover Dam is written not just in numbers, but in vigilance that continues to this day. The structure is alive with sensors, strain gauges, tilt meters, and piezometers, buried deep inside the concrete and bedrock. These instruments track the slightest shifts, from the gradual settling of the dam to the pressure of water at its base. Over the decades, data has revealed that the weight of Lake Mead can actually flex the earth beneath. The crust beneath the dam dips by about 0.6 inches when the reservoir is full, and the dam itself settles roughly 2 millimeters under load. Modern monitoring teams walk the inspection galleries, reading gauges, and logging every movement. The dam's safety depends on this constant watchfulness. The sacrifice of those first builders is honored by the engineers who guard the structure now, turning tragedy into a legacy of precision and care. Right now, over 40 trillion gallons press silently against a wall shaped by physics, not just concrete. The real safeguard is ongoing vigilance. Engineers still monitor every crack and shift. It's a reminder, nature's forces never rest, and neither can our attention. The margin for error is always razor thin.